Hi, my name is Allison Vermock, and this is my Lab 2 presentation about analyzing the motion of a falling object. Before we start, it is important to note that the main concepts covered in this lab stem from Newton's second law, which states that the net force acting upon the object is equal to the change in momentum divided by the change in time. This law translates into the velocity and position update formulas, which will be used later in the computational models to update the velocity and position of my object. These updates are impacted by two main non-contact forces. The first force is the gravitational force that attracts my object, a banana, towards the Earth, and the second force is the drag force, which opposes the downward motion of the banana. Since there are numerous forces impacting the system, the net force is not equal to zero. So when calculating the net force of just gravity on the object, the net force is equal to the gravitational force. And when calculating the net force of the object with drag, the net force is equal to the combined gravitational and drag forces. For the lab, I recorded a video of a small banana falling from rest, then analyzed the position over time in Tracker, then calculated two computational models in GlowScript, and finally visually compared the observational data to the computational data sets. For my Tracker video, I chose to use a banana with a mass of 0.118 kilograms as my falling object. I chose it because it had a decent surface area and was small. I oriented my axis so that it would track the banana falling in the negative y direction, and started tracking the motion of the banana as it fell from the 65th to the 82nd frame. The overall time was a half a second, and the object fell for 1.36 meters. Then I edited my Lab 2 code to include the banana's mass, the initial starting position, and the proportionality constant for the magnitude of the drag force. For the model without drag, this value is 0. However, for the model with drag, this value is 0.038. I calculated this by editing my gravity-only data and plugging in b-values until the total distance it fell was equal to the height it had fallen in Tracker. Now in the loop, I included formulas for weight force, the drag force, and the net force. Next, I included the velocity and position update formulas from Newton's second law to iterate through to the next position and velocity value. Later in the code, I had to calculate the arrow scale and did so by dividing the distance fallen by the magnitude of the weight force. This value came out to be 1.177. I ran the code, and as you can see in the image on the left, there is no drag force opposing the gravitational force, and the banana fell a total of 1.57 meters, about 0.2 meters further than it did in Tracker. On the right, there is a drag force, as shown by the blue arrow pointing up from the ball, and this caused the object to fall 1.36 meters just like it did in real life. Both of these graphs look similar, but when I put them on the same graph, I noticed that the computational model with drag was similar to the computational model without drag towards the beginning of the fall. However, it was more similar to the observed model towards the end of the fall. I concluded that the observed and predicted with drag models were most similar to each other overall because they started and ended at the same points and had a more similar slope that began flattening out towards the end of the curve. The model with only gravity fell further than the models with drag because it didn't have an opposing force acting upon it. Some errors I saw arise in my lab as a result of the visualized data, where I might have tracked my centers of mass incorrectly in Tracker because of the object's oblong shape. The slope might have been more accurate if I had analyzed more than 17 frames, and the object in Tracker moved slightly in the x direction. So, which model best predicts terminal velocity? Well, if terminal velocity occurs when the acceleration of a falling object is 0 due to the gravitational force and the drag forces being equal and opposite, then the models that include both the drag force and the gravitational forces acting on the system would be the most accurate models. This can be seen in the velocity versus time graph, where the slope of the yellow curve is flattening out to 0, thus reaching an acceleration of 0, and thus approaching its terminal velocity. Finally, what if the object was thrown downward initially? How would this impact the terminal velocity? Well, in short, the object that is thrown down would have a larger drag force initially because the object is already accelerating downward. Because of this, the terminal velocity would be reached faster. However, the value for the terminal velocity itself will not change. This can be seen in the graph since both curves have almost identical slopes, and the one that was thrown with an initial velocity, shown in green, traveled further and leveled out faster than the one that started from rest. This concludes my lab presentation. Thank you for watching.